All right, next, we're going to solve problem 1.31. Calculate the volume integral of the function t equals z squared over the tetrahedron with corners at 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So I tried to draw it here. So 1, 0, 0 here, 0, 1, 0, 0, 0, 1. So this is my tetrahedron. So now the function is t equals z squared. So I need to determine the tau, which is pretty easy, Cartesian coordinates, so dx, dy, dz. Well, the remaining thing is determine the integration limits. All right, I created a little model just to visualize this a little better. So this is my tetrahedron. This is the origin, x-axis, y-axis, z-axis, and these are the respective planes the faces are parallel to. So the last face is important. I'm going to add that in a moment. So if I want to do the integration limits, I mean, first thing I can observe is as x goes 0 to 1, right? I can start from here. But then for every x value, where does the y limits lie? Well, they start from 0, goes and hits this line. Well, that's, on the xy plane, pretty easy. Okay, if I put this as y and this is my x, it's the line that cuts y and x at 1, right here. So I can, easily write this line. It's 1 minus x, right? Its slope is -1 and cuts y-axis at +1. So this should be it, and it works. So now that means x goes 0 to 1, y goes 0 to 1 minus x. How about z? Well, for z, right, if I take any point and then I'm integrating, you see, you go up and then you hit this final surface here, right? This is your surface. Okay, so we need to, this plane, this fourth face of the tetrahedron, we need an equation for that so that I can write z integrate. I mean, it starts from 0 again on the xy plane, but when you go up, you hit this plane. So what's the equation for that plane? That's what I need. How do we determine equations for the planes? Okay, well, if you have the normal vector and any point on the plane, your job is easy, because any point on the plane, I can say, okay, x comma y comma z. And any point that is known, these are the corners, any one of them I can take. Well, so I can write a vector on the plane, and that's perpendicular to the normal to the plane. So any vector on the plane, well, I can determine that by, okay, position vector of any point on the plane would be this, right? And then one of the points, let's say the corner at the on the x-axis, that would be say r0, which is nothing but x hat, right? 1 x hat, there is no y hat and z hat. So that means r minus r0 must be a vector on this face of the tetrahedron, which is given by x minus 1 x hat plus y hat plus z hat. So that's what it is. Now, if this vector is dotted with a normal vector, well, in this case, it's a very symmetric case. Normal vector is obvious, right? Normal vector should be, in this case, something, that has equal components in the x, y, and z because of the symmetric situation of this. So I can write the normal vector as x hat plus y hat plus z hat, say square root of 3. That's the unit vector along the normal. So if you do a dot product of them, you need to get 0. So I can write 1 over root 3, x minus 1 plus y, y times 1 is y, plus z equals 0. So this, okay, you multiply both sides. I mean, this is not relevant really. You get basically x plus y plus z equals 1. This is the equation for the plane. So that means I can write z as 1 minus x minus y, right? That's what determines the z coordinate. So my integration limits for z should be 0 to 1 minus x minus y, right? All right, so I'm ready to write the integral then. Integral t tau over the volume of this tetrahedron. So I have the z, okay, z, okay, so we should start in the reverse order. Okay, x will be the last, and then y, and then the z, which is 0 to 1 minus x minus y, and then it's z squared, right? That's the function. And then I'm going to take the y integral, which is 0 to 1 minus x. By then, everything will be in terms of x, and x will be 0 to 1. Okay, so this is 0, this is y, right? That's what I'm going to do. Okay, the first one is pretty simple. And we can write it out easily. All right, so equals x 0 to 1 dx, y 0 to 1 minus x dy. Now z cubed over 3 evaluated at 0 and 1. No, 1 minus x minus y. So what do I have there? X is 0 to 1 dx, y is 0 to 1 minus x dy. Now what I have here is 1 minus x minus y cube over 3. Now I'm going to do a y integral. So to do the y integral, of course, I can do a little substitution here that might make life very easy. So 1 minus x minus y is u, minus dy is du. Okay. So integration limits change accordingly. If y equals 0, u becomes 1 minus x. If y equals 1 minus x, y equals 1 minus x, u becomes 1 minus x minus 1 minus x, u becomes 0. Okay. I think that's about it. So x equals 0 to 1 dx. Now I have u equals, well, there's a negative sign here. I can still switch them. U equals 0 to 1 minus x. And then I have u cube over 3 du. Okay, let's do that. X equals 0 to 1 dx. And if you do this, you'll get 1 minus x cube, oh, to the, okay, u to the 4th over 4th power. So 1 minus x to the 4th over 12. Okay. And now the final integral. Again, can expand this, or we can do a u substitution. I find that easier. 1 minus x, I can call, let's change the variable t, and minus dx is dt. So t to the 4th over 12 and dx, and then integration limits x equals 0, 1 minus x, which is t equals 1. Right? And x equals 1, 1 minus 1 is 0, so t equals 0. Again, this negative sign, but it changes. So t equals 0 to 1, or 1 over 12 here. And u to the t to the fourth dt. Okay, what is that? T to the fifth over fifth, 0 to 1, 1 over 5, now 1 over 60. That's what we get. All right. I think that's the solution. I hope you enjoyed it.